当然没有每天在当顾问啊，那么好，回一次。OK OK, we start from here again. Okay, this different kind of chessboard, different kind of chessboard, and the one I show you is this one is the easy one. But all I mean the purpose for different kind of chessboard are the same. So we start from here. So basically, right, this one is a previous what I say here, right? This one we start from here, from this one, and we start to solve the intrinsic parameters and the extrinsic parameters. Okay. So right now is on page 27. Page 27. So input is this one. Output is this one. Okay. So what is this one? This one is 3D position. For each corner position. So this board, assume this point is 0, 0, 0. Assume this point. This point is 0, 0, 0. And the second point is 2 centimeters. So the unit will be centimeter. So this X, this Y. So X, Y, and Z will be the other side. X, this Y. So X, Y, Z will be, and this side will be minus Z, 负 Z 这个方向 X, Y, Z， 那这是负 Z， 那还好。So the second point, this one, will be 0, 2, 0, because this Y direction. And the unit is centimeter. So this point will be 0, 2, 0. And the other side, this point will be 2, 0, 0, something like that. So this is, you'll find out all Z are 0 because this is a plane. So all the Z, these are 0. And this is unknown. This rotation, this translation, this is intrinsic parameters. What is this one? It's if I do this one, you take a photo. So in this one, in this image here, this is a photo you take. And in this image, this corner, the top left corner will be 0, 0, 2D. So this is UV image. In your top left corner, this one will be this one. In this side will be 0, 0. 这个会连连。这里连连。So in this image, any corner position here. 我刚刚讲错了，抱歉啊。This will be 0, 0 here. Sorry. In 3D, there will be X, Y, Z. 看不到啊，鼠标看不到，什么意思？看不到我手。哦，真的、哦？那我怎么办？哦，这不要移过来，就在这里这样。我的哦，指这里这样子，所以你们看不到我的这个哦，只要看这里，但是你看得到我的画面，但是看不到我指的东西。那我再讲一遍，刚刚讲错了，我来从头讲。 因为左右颠倒了啊。那个但只这里看得到了啊，这里 OK。So in 3D, what's the x, y, z？ 我把背景拿掉了，这背景真的是真的哦，我不要虚拟背景。好，这样比较，哎，sorry，可以啊，这个后面很丑。I say again. Sorry. I say again. Okay. So x, y, z here is meaning 现在不晓得到底怎么左右颠倒。就 first of all, I say this one first. Okay, this image, right? So image in this image, you see is image. So in your top left corner, this left corner is 0, 0 on the top left. So any position here is a in this image that is a 2D coordinate. So probably like this point, probably 100, 100, because this is x. So this side x, this one is y. So x, y, this will be z. So z will be in your the positive z will be your direction. So the previous essay is just upper size. 我讲错了嘛。So let's say again, this is x and this is z. So xz. So sorry, x and this y. So x, y, z will be that this will be positive in your direction. So in the image, this side is that top left corner is 0, 0. So any point here is based on the top left corner. So this is a 2D position. So 2D position is this one. Okay. And what's x, y, z? It's a this plane itself. 这是 plane 它自己本身 object 本身，跟其他都没关系。那所以里面这一点是0 0 0 0 0 0 0 this one this point 这是000，那所以这边也是 x y， so z will be that direction z, so this will be 0 0 0, and this y so it will be 0 2 0, and this x so this point will be 2 0 0这样子上过去。So this is 3D, this one 3D, and this is a 2D. And suppose here, I don't know how many points, how many corners. I just assume there's a 40 corners. 假设现在就是很难去哦 ，OK，好吧，好吧，那市场00是在这里的，然后影像是在这里的啊，嗯，好，没关系，先你们知道就好了，然后是怪的关系，好 ，OK。Now, the other one is that we suppose assume there's 40 corner points here. 假设40个点. So here will be 40 points here. This corresponding 40 points here. It's 40 points here. So this is 4 by 3, right? 3 by 4, 3 by 4. And this will be 4 by 40. 这里会有40个点。这4嘛，4 by 40，这有40个点会在这里。这样可以啊。那这里会有40个点在这，40 points here. So this is not a vector, this is a matrix. And this is a matrix. 这样子. Okay. So we keep going. Because this is plane, because it's plane, so we assume the z equal to 0. Not assume, just z will be equal to 0. Because z equal to 0, so we don't care about the R3 z rotation. We don't need to care about that, the z rotation. So become this one. But we can recover the RZ based on R1 cross R2. R1 is Rx, R2 is Ry. So based on the cross product YG, you can recover R1 and recover R3 based RZ based on R1, R2. Later we'll do that. So we can ignore the R3. So right now our unknown parameters are here. Is A is intrinsic parameters. Your extrinsic parameters are R1, R2, and T without R3. And this right now because we try to solve this one. So we will try to change this format to homogeneous matrix. 我们要把它改成 homogeneous matrix 形式. So this term will become H. Homogeneous, so it's H. So this equation will become this equation. And this S is scaling term because it's homogeneous. Scaling is meaning you can multiply this one, S1 to here, S1, SU, SV, S1. 这个可以把它乘进来的意思啊。那这是一个 scaling term， homogeneous scaling term， 你这样可以乘进来就变成只有一个 term， so become SU, SV, S. So this is only one term. So this will be H times M equal to small m problems. This will be X equal to B problem, this one. Okay. 这样可以哈。So far, so the equation, this original equation, because we try to solve this one, the intrinsic parameters. So we change the format, become AS equal to B is this one. So we can start to solve H. Okay. So we try to solve H, this one. Here. We try to solve H here. But we talk about this one later. We step by step. 目的是要变成这个形式，把 this unknown and this known. So become AS equal to 0 problems. We can solve it. But before we solve it, we back to here. Okay. So here we do again. We do again. So this one, right? This part become this part, equal this part, original this part. 这我把它写比较详细一点啊，那你比较了解。这我把它写详细的啊，就这个等于是一样嘛，3乘3的 matrix。那 because it's a homogeneous matrix, so your equation format will become this one. Right? It's homogeneous matrix format. And if you do the equation format, it will become this one. But the one we try to solve is M is ground truth. M head is an estimation, prediction estimation. So M minus M prime, N head will become UV will be ground truth. So what's the N prime? N prime is here. This equation format is this one. So become here. So M minus the ground truth minus this M. This M equal to this M. This M equal to this one. So become this format. Okay. And that's this format. And this format, okay, this format, because we try to solve H. So this format will become H is unknown. And M, this M is M prime here. I'm sorry, here. This one, H is unknown. M is 3D position. UV is 2D position, corner position. So we reorganize this one, will become this format and equal to 0. So this format become AX equal to 0 problems. I say again. This one, right? This is this one. Right now, I say again. Right now we have this format. But this format we reorganize to be this format based on the equation format. But 这是整理，这不是叫你算了，这是我们在私底下在算的时候，怎么去凑成这个东西的。I say when you write the program, don't write equation. But this is when you do calculate on your spreadsheet， 在外面在做，因为你要目的是要变成 x 等于 equal to b 的形式的，所以在旁边笔要先写一下。所以我们这个形式，我们把它重新组织，这是 equation 的形式，这人家推的，我只把它偷。那这个形式变成这个，那这个就是我们的 equation 的形式。那 our purpose is this one. M is ground truth， 就是你的 M is the ground truth is the corner detection result. This is your estimation. So this equation will become this equation. This equation will become this equation. And UV is a corner detection result. M is 3D. H is the unknown parameters. So based on this one, we reorganize, become this one. H is unknown. 就我们把 unknown 的放一边嘛，已知道放一边。So you know 3D M, 2D UV. You doesn't know this one. So become AX, here's LX equal to 0 problems. So we can, this is homogeneous format. Original format is this one. But this one, they try to reformat, reorganize, become this format, and they can solve H. This one time AX equal to B, AX equal to B. But they don't want to solve it. They want to solve in this format, in this paper. So they reorganize, become this one. So AX equal to 0 problems. So they can solve H based on 2D, UV, and 3D M. Okay, but this page, we try to let you know. We do this one, sum square difference problems, right? We talk about sum square difference problems. We also talk about mean square difference problems. Here, I want to let you know is they ignore this term. So when you see the sum square difference or didn't mean square difference, actually the equation is not original equation. It's incorrect. 你看到 mean square difference 或那个就深度学 mean square difference 或 sum square difference， 基本这个不是原来的 format， 这是错的。原来的 format 是这个东西哦。那这个东西是什么？是 the Gaussian the exponential term of Gaussian distribution。写给你看。So for this lecture, I keep mentioning about the Gaussian distribution, right? So the probability. 这样看得到吧？会不会颠倒？为什么看到我都是颠倒？没有颠倒啊。OK，好，来，You see the whiteboard? Okay, so this is the Gaussian distribution. So given, given a small image, 20 by 20 pixel, whether there exists a face or not, given given a small window, 20 by 20, whether there exists a face or not. So this one equal to the Gaussian distribution, right? So this is normalization term. This is 正规化的 term 嘛 ，square two pi, right? 2 pi square root times standard deviation, exponential term. And this term is minus half 2/2. This term, the exponential term, this term is this term. If it's a m and if it's a m and n head here will become m and m head， 这会一个 m 一个 given 估计嘛，估计 given m head 这个，然后你存在 m 的几率是多少 ？given m head 存在这个，所以这个 term 就是这个 term。given this one estimation and once it exists the ground truth 这样子。m is ground truth， 就给定一个小 window， 它存在人脸的几率是多少 ？Given a small window 20 by 20, what's the probability？ 来板看起来比较小，我走，看起来比较小，可是我已经啊写大一点，啊就 let me check。I try again. Sorry. Is that okay? I'm sorry. Okay. So given 给定 this is an n prime is estimation. Okay. And you try to estimate whether this ground truth. So if I write so that's mean if I give an image, small image I, this page 20 by 20 page 20 by 5 pixels, and whether they exist a face or not， 我给定一个小的20×20的 page 影像 I， 那我这里存在人脸的几率是多少？这样子，那一模一样，所以这是 normalization term 嘛，就等于这是 2 派是 standard deviation， 然后 exponential term， 然后负1/2，然后这个矩形这个 term 就是这个 term， 一模一样。等一下哦，那我再继续讲。 So exponential term this one. This exponential term this one. Actually is equal to this one. 负2n-z，然后这是 I 减 f I minus f square 平方，是一模一样。啊，那你的 I 刚刚讲的 I is a estimation， 所以这个是 m， 这个是 m。这是 estimation， 不知道的嘛，你给那个 estimate， 然后 this is ground truth 是存在 phase 的几率，是跟这个式子一模一样，是这样子。然后 this one is a covariance matrix， 在分母。啊，那 covariance matrix 的话，基本上 in this case will be就变成这样子，这样看得到吗？This a denominator term， 啊，这个 standard deviation square and this a standard deviation square， 这样，分母的 term， 就是这个是个嘛，是分母。那因为一般来讲，我们的the Gaussian distribution is this one, right? The Gaussian is the standard deviation square, and x input x, pixel x, and this mean, right? So the mean is standard deviation. 这是一般高勋的 term 是这样。The regular the Gaussian distribution, the exponential term is this one. And this is your standard deviation square, so variance. This is variance. This is your mean value, right? And this is the input x. 这样子。This is the Gaussian distribution. So that's a Gaussian model. So the Gaussian model, the exponential term, this term actually is equal to this term. Exactly the same. 这两个是一模一样的。只是呢，这是高勋的话 ，this is mean， right？ 那这里就把 mean， 把这两个，一个是 input， 一个是变成是那个估计值嘛，所以是 one is m，one is m head， 所以这个是改成我们刚刚讲的那个红色写的那个形式，两个是一模一样东西，两个是一模一样东西。So this is a Gaussian model. Now right now I try to explain to you is this one. But no matter is some square difference or mean square difference. Okay, it's from this one. What is this one? This is the Gaussian distribution, the Gaussian model. So what is the Gaussian model? It's a likelihood. It's a likelihood. 啊，我刚讲错了，这两个是写颠倒了。I teach you the base theory. 好像刚刚有讲错，应该是讲这贝氏定理的东西 ，Bayes theory。So the likelihood, sorry, the likelihood term is this one. So that one I say this wrong. 那我讲错了哈，刚刚讲那个是 likelihood 是这个 term，所以这个 term 的话 ，I 这是 I。The one on the lecture PPT, this one will be likelihood is this term. So this is likelihood term, and this is prior probability, and this is posterior probability. This posterior. So sorry, previous I told you is this term, no, is this term. So the one shown on the PPT is likelihood term. Likelihood term is Gaussian distribution. The Gaussian distribution will be this term. It means the similarity between F and I. Okay. Posterior probability is a given a I, unknown I, that's 20 to 20 pixel. Whether there exists a phase or not, this is called P-O-S-T-E-R-I-O-R. This is called posterior probability. Posterior probability equal to proportional to 正比于 likelihood times prior probability. Prior probability 就是说 posterior equal proportional to 不是 equal proportional 正比于 likelihood times prior 预期的 prior probability F 人点 F. So I say again, the purpose is we try to given a small window I, whether there exists a phase or not. This probability is the final answer we want to have. Will be proportional to likelihood. Likelihood, we will say the similarity between F and I. The similarity between F and I, and times prior probability. And I will teach you this one more in detail in later, not this lecture. So the Gaussian model is likelihood. Likelihood meaning the similarity between both. Given small window, whether this one, and with your template, your data, your ground truth, both are what's the similarity between both? 两个的相似度是多少？这是我们称为高勋 model。那高勋 model 本身是一个 likelihood， so this one is a likelihood。我刚刚讲说是一个 likelihood probability. That means the similarity between this one and this one. But in Gaussian model, in the denominator term we have this standard deviation. So what's the purpose for standard deviation? It's for normalization. So I keep tell you, okay, because sometimes this unit will different from this unit. So you need to divide it by standard deviation in order to have both unit are the same. 我一直跟你讲说，我们在做任何的评估的时候，像normalized cross correlation， 为什么分母都要除一个标准差？是因为在这个环境下，光我们讲光那个单位不一样，是有时候在这个环境下，光线 lighting is different from this lighting. So in order to let both have the same situation, as a lighting situation or rotation situation, we need to divide it by standard deviation. So that's the Gaussian distribution. The same as eigenvector and eigenvalue. eigenvector into divided by eigenvalue. So that's direction, that direction, the unit will be the same. Okay, so eigenspace is the Gaussian model. This one is also a Gaussian model. So theoretically, we need to divide it by corresponding standard deviation square that's been divided by variance. But because most of paper or most of papers say, I assume both situations are the same. Both situations are the same. So they ignore this term. It can become identity. So in this term, they ignore the standard deviation. So when you see the mean square difference or sum square difference, they ignore the denominator term because they assume the lighting situation, the environment are the same. But is that true? No, it's not true. OK， 所以这个要小心哦，这个是假设，所以你看你现在看到的，不管是 mean square difference 或 sum square difference 是假设，我不处理光线，那怎么办？这里不处理，那高勋 model 是写下来，看一下上面那个，对，对，这样子，我写给你，我再写一个，看看啊。Gaussian model is this one. Posterior is a given right. Posterior is given this unknown and this ground truth. Given the thing you don't know, there's estimation. Posterior is given unknown. You don't know this one. And this one exists a phase. The probability exists a phase. That's posterior. You want to estimate the unknown thing. Given a small patch, you want to estimate the probability whether it exists a phase or not, a phase. And the Gaussian distribution is likelihood. Likelihood meaning the similarity between both. One more difference because they have one more prior probability term here. So likelihood times prior probability or proportional to the posterior probability. That's a Bayes theory, Bayes 定理。Okay. So right now, what you did for us, no matter is sum square difference or mean square difference, actually they ignore the normalization term. So it's incorrect. So when you do the deep learning, because you're deep learning the gradient descent, you use a mean square difference, they ignore this term. So what will you do? So you'll find in the beginning of input, they do the normalization. For a deep learning, okay, because they ignore this term, so the result will be incorrect. So how do they do? So before the data input to the network, they do the normalization. 就是说，我们在做深度学习，你会发现，哎，很多深度学习的处理，它变前处理了。它 normalize 是在前处理就把它 normalize 完了。你会发现它只是介负1到1或0到1嘛，因为它在那边处理掉了。它处理光线，它不管是处理0到1或负1到，它不是都处理一个 standard deviation， 都减掉一个 mean， 也是高勋 model。所以在 deep learning， 它事实上不在 gradient descent 那边做。它是在输入 data 那边把这些程序把它做完了，是这样子，自己要注意哦。不是把原始 data 那个 when you do the deep learning, they do not put the raw data into no, they do the pre-processing because in their those function they ignore this term. So that's very important. Okay. So this also have one very famous likelihood we call Mohanlabus. This is also famous. We call Mohanlabus distance. This is known. So this one actually from this one. The difference root. 就你这个注意，这有这个名词哦，这也是评估 likelihood 的，叫 Mohanlabus， 它基本上就是跟这个一模一样，只是它多一个 square root 这样子。这是 machine learning 的东西，你看一模一样，上就是这个东西，只是它多一个 square root， 这是 some square difference， 然后是 square root 的 difference 这样子称为 Mohanlabus 这样子，可以哈。好 ，so we back to they don't use this one. In this case, they use this case. Ignore the normalization term. So we solve this one. So they use AS equal to 0 problems. So how can we solve H? So how can we solve H? So you see the M and the image UV is like this one. 我帮你写了，我帮你推导了，这样就是这个式子。那你要解 H. So how can you solve H? Actually here, they talk about here. It's from L, they do SVT equal to UWVT. And they find this one, they find the W equal to, close to the 0, corresponding eigenvector. So, let's see, eigenvector, the eigenvector of this one associated with the smallest eigenvalue, and this eigenvector will be your answer of H. That's your solution. But why? Why this one? 我把它讲完了，是这样子，大家讲一下。X 找出一组 eigen。This one. Your purpose. You try this one. The equation Ls equal to 0 is here, right? Ls equal to 0. This one. Lx equal to 0. And you try to find this H. X is H. Try to find H. Which H? Well, that this equation equal to 0. So based on the L, you have a U, W, VT, and U is the eigenvector, W is the eigenvalue. So they have many when you study the eigenspace, they will tell you it has many solutions, not only one solution. So we need to pick up one solution for this situation. So this situation is when you find one eigenvalue, this eigenvalue close to the 0. Well, this one is close to the 0. So when you find one eigenvalue, the close to 0 eigenvalue corresponding to the eigenvector, this eigenvector will be your answer. 听得懂吗？你的目的是要让，因为这是你的目的是要让解这个嘛，解 h 嘛，是 x， 你要让它等于0。那你有用到我们用到 UVW 的话，用到 eigenspace 的话，你会发现 eigenspace 是跟你讲说，我不会有唯一组解，我有很多组解。那这么多组解哪一组解才是你最要的？你的最要是你希望你的解是等于0，所以你会找 eigenvalue 接近0的这个 eigenvalue， 它对应一个 eigenvector， 这个 eigenvector 就是你的解，因为它很多 eigenvalue 嘛，那每个 eigenvalue 都对应一个 eigenvector。那你这个状况就是你会找最接近0的那个 eigenvalue 对应的 eigenvector， 就是你的 h， 这样子。他用这种方式来解 Lx equal to 0 problems 这样子。好，那我先它里面再跟你讲这个问题，这下面再跟你讲这些答案。那我们待会再稍微提一下这样子。OK， 我们先下课，谢谢。